energy. Chemistry, we study the atoms and the molecules, but there's also energy involved in the changes that they undergo, so we have to study a little bit of energy. In science, we define some terms a little differently than the way we use them in everyday life. Energy is the capacity to do work. And work is defined as the action of a force through a distance. So that's really different than what we describe work as in our everyday lives. Say, well, I did a lot of work today. Well, you did something that was probably not something you would have chosen to do. You did it because you were getting paid for it, right? So that's kind of an implication in work. But work in the scientific sense is moving an object through a distance. So this guy pushing a box is doing work. When I lift this marker up, I'm doing work. Did I get paid to lift the marker? No, not directly. But moving that, I'm applying a force through a distance, and that's what work is. When you ride a bike, you're doing work. When you walk across the street, you're doing work. You're applying a force across a distance. Energy, again, is the capacity to do work. There's different forms of energy. Kinetic energy is associated with motion. Anytime we have the word kinetic, it has to do with motion. And potential energy is energy associated with the position or the composition of an object. So here we have an example of a 10 kilogram weight sitting at the edge of the top of a building. Now this has high potential energy. It's unstable. This reminds me of the Bugs Bunny cartoons. They're always dropping pianos on people. What's going to happen if this gets bumped? It's going to fall, right? It's not stable up here. It has a great deal of potential energy because of its high distance above the ground. If we bump it, as it falls, it begins to move faster and faster. The potential energy that it had here is being converted into kinetic energy as it moves faster and faster. Something moving faster has more kinetic energy than something moving slower. Then, eventually, it's going to hit the ground. Now, down here, it's got low potential energy. It's pretty stable down here. It's hard to fall off the ground. You can't fall down if there's nothing below, right? So this one's pretty stable now. But what happened to the energy? We'll find that energy does not appear and disappear. The kinetic energy, well, let's start up here. Potential energy was turned into kinetic energy. When this hits the pavement, the potential energy gets turned into heat energy. Now, you may not be able to detect that heat energy with your five senses, but there is a slight temperature increase when that happens, when there's a collision. That heat energy is thermal energy. Thermal energy is the energy associated with the temperature of an object. And it's actually a kind of kinetic energy. It's related to temperature. The temperature of an object is a measure of how much the particles are moving. So if we think back to the solid state of students, right now I'd say you guys are at a pretty low temperature. Everybody's just kind of chilling. Right? You're sitting pretty still. What if we were all really agitated and we were fidgeting and wiggling, right? That would be a solid still because you're in fixed positions relative to each other. It's a solid. But now you're moving a lot more. The temperature of that solid is higher. So if you have like a hot brick, the reason that it is hot is because the particles in it are vibrating more violently. In a liquid, so liquid state of students, during lab you're walking around. Low temperature, you're walking, which is what we should do in lab. If we heat you up though, you move faster and now you're running around the room, which is not advisable in a chemistry lab. But that's a higher temperature. So thermal energy, which is related to heat, is actually a form of kinetic energy, but the movement is in the individual particles, not in the big block of matter as a whole. That big weight fell off the building. The weight had kinetic energy as it was moving. It hits the ground, all that kinetic energy goes now into individual movements of the particles, and the temperature of the weight goes up. So we had an introduction to what laws are. Here's a law of conservation of energy. And it states that energy is neither created nor destroyed. We can change energy from one form to another, from kinetic to potential and back and forth. Energy can flow from one object to another. If you have cold ice cubes and you put them into warm water, the warm water has more thermal energy, and that energy flows into the ice cubes and warms them up. But the total quantity of energy is constant. So there's no such thing as a perpetual motion machine. You cannot generate energy out of nothing. The energy content of the universe is constant. Objects that have high potential energy tend to be unstable, like a piano hanging out of a window. But we can also have chemical potential energy, and this is from the forces between the particles. So things like gasoline and TNT have a great deal of chemical potential energy, and they are unstable. They can explode. Whereas something like water has less potential energy, it is not unstable. So energy is always conserved in physical or chemical changes. Systems with high potential energy tend to change in a direction that lowers their potential energy. And when that happens, energy is released into the surroundings. You think about your car. You put gasoline into your car engine, right? There's a lot of potential chemical energy in the gasoline. And you burn it in the car, and it makes the pistons go up and down, which goes through some things and makes the wheels turn, makes your car move. Is that a 100% efficient process? Does all of the potential energy of the gasoline get translated into kinetic energy of your car? No. The engine gets hot, doesn't it? Some of that energy is lost. We say it's lost because it's not useful anymore. But it's not that it has disappeared, but it dissipates as heat. And your tires rolling on the ground experience friction, and they get warm. And so some of the energy that was originally in that gasoline is lost to the surroundings or released to the surroundings as heat energy. So the more efficient a process is, the more of the original energy gets translated into something useful. And something that is inefficient, more of that energy is lost to non-useful things.